So let's solve this problem using continuous and discontinuous Galerkin on an Excel sheet, and we have already solved this previously. So I would just modify the existing Excel sheet. Just the difference that I have made is instead of linear elements, I have again considered 3 elements, but I have used quadratic shapes, which means that instead of 4 nodes, I would have 7 nodes with 3 nodes in every element. And I'm using a 2-point Gauss rule inside every element, so there will be 2 Gauss points on which we will compute the shapes, and so there will be 3 shapes for 3 derivative shapes and 3 test function, trial function shapes inside every element. So let's just do this on an Excel sheet. Before that, let's look at the formulation. So this is our continuous Galerkin formulation, and mainly we have to assemble this term, this red term, grad V dotted with grad U, and grad V forms the rows, which would be like 3 rows into 1 column, and grad U would be expanded into 3 columns and 1 row, right? So that would come from the solution approximation in our finite elements. So to assemble this, we would just multiply. So when we assemble this, we want a 3 by 3 matrix. So we would just multiply this 3 by 1 vector, 3 rows 1 column, with this 1 row by 3 column vector, right? So this is basically just your grad V into grad V transpose, which is exactly what we have done in this Excel sheet. And this is this is a useful hack even for coding, for writing your code in MATLAB, Python, or Julia, or you could also do this on Excel very easily, very quick way to assemble. And we would also use this for assembling our edge matrices. And this makes the data structure very easy, and you can just translate this to code very easily. So here you can see that I have already plotted the continuous Galerkin solution, but let me show the assembly. Before that, let me just look at the basics. So this is our node and x coordinate. So as you can see, these first 3 nodes are our first element, 3 to 5 are the second element, 5 to 6 are the third element. Our master element is running from 0 to 1, at which we have these 3 quadratic shapes and their derivatives, and we have defined 2 Gauss points as per the 2-point Gauss rule, and we calculate these shapes at Gauss point 1 and Gauss point 2. We have our Gauss weights here, and finally now let's look at this assembly, which is just grad V into grad V transpose, right? Let me assemble this once in front of you so that it's very easy to see. So this is your first Gauss point, grad V at your first Gauss point, multiplied by transpose of the same array, multiplied by Gauss weight 1, multiplied by your scaling, which is basically your step size, which is also divided by your step size twice, because you have 2 gradients, which means that you just have 1 upon your step size, which is 0.33, which is just 1 upon 3 basically. So you're just dividing by 1 by 3, right? So this is the first part, and now let's just also add the second computation for the second Gauss point, transpose of second Gauss point multiplied by Gauss weight into 1 upon 1 by 3, right? So you're getting this exact same matrix which we have here. And so now let's just quickly do this assembly very fast, very easy. We just add these guys here, and this is singular because we have not imposed the boundary conditions. So let's put 1 in the force vector here. So we have 1 in the force vector. So this would impose our Dirichlet boundary condition. Right. So this is our CG solution. Very simple. Now let's look at how we would assemble this for the DG case. And for the DG case, of course, let me just zero this out. So this is our stiffness matrix for the DG case, but we have to look at the assembly first. So clearly this guy is really the same. First, the interior assemblies, the interior integrals. Let's look at our DG formulation. So this is our DG formulation. So this blue guy here is just your integration inside the element, right? So this is really the same, grad V dotted with grad U. So here we just have to pick this up and add it as is. So now we have to assemble our edge matrices, and for this we have to look at this yellow block here. So for this we have to create a 6x6 matrix which will add here for the first two elements and here for the second and third elements. So this would be 6x6. So let's assemble our 1x6 arrays or 6x1 arrays, right? So how do we do that? So let's just consider that we are at point 2. So we would have 3 vectors from, or rather 3 shapes from this side, left side, and 3 from the right side. And if we are evaluating those shapes at x2, we would just get 0, 0, 1 and 1, 1, and 1, 0, 0, right? Because the first test function is basically 0 at this node. Let's have a look at those test functions. So these are your quadratic Lagrange shapes. And if we were looking at this blue guy here, so this guy would just be clearly 0 at this node. The yellow guy would be 0 and only the orange guy would be 1. And similarly the purple guy would be 1 and the rest of them would be 0, which means that we can just assemble our 6x1 matrix as 0, 0, 1, 1, 0, 0. And similarly the jump across this would just be a minus sign onto these 3. So you have 0, 0, 1, minus 1, 0, 0. Similarly, we can also evaluate the gradient of V by just evaluating these shapes, which are these guys. These are not clearly 0 because we are using Lagrange polynomials, which are C0 polynomials. They are discontinuous. So you are having these shapes here. So they are different at both of these boundaries. And let's just evaluate it. So to evaluate it, when you are on the left side of the element, this side, you would just evaluate the left side functions at 1. And when you are on the right side, you would evaluate all of these right side functions at 0. And when you do that, you would get this gradient of V. So I'm not showing this computation again. And to get 0.5, the 0.5, which is basically your average of your n dot gradient of V. So how do you get n dot gradient of V? So we just multiply by n, which is just 1, 1, 1, and minus 1, minus 1, minus 1. Because on the left, because on the right side, the unit normal in the outward direction is minus 1. So we just multiply by that. And to take an average, we multiply everything by 0.5. Because when you add up, you are just combining the elements from both the sides, and you're just taking an average. So which means you just multiply everything by 0.5. So you get these 6x1 vectors. Okay, and now we can just use them to assemble our 6x6 matrices. So that's what we have done here. So the first guy is this one, jump of V multiplied by average of flux. So that's what you're doing here, jump of V multiplied by your average of flux. So the average of flux is transposed. What do you have here? You have your second term, epsilon, which is here epsilon is just +1, and average of v multiplied by jump of u, average of v multiplied by transpose of jump of v here, which is your jump of u, right, in this case. And then you add up both of them, your integration by parts term, which is this term, and your symmetry term to get this. You could also put a minus sign here if you want at the non-symmetric case. You could just do this minus, because right now it is symmetric, as you can see. So I can just use this minus, and this would just make it non-symmetric. So this is our second term, and the third term is the penalty term, which is just jump of u into jump of v. Jump of v into jump of u. So that would be again the jump of this guy, basically this 6 by 1 multiplied by 1 by 6 again, divided by your step size and multiplied by your penalty. So now we simply have to add these guys here. So this guy has to be subtracted because you have a negative sign. These two guys, they have negative sign, so let's just subtract this from each side. Subtract. Let's impose our strong boundary conditions first. So this is more visible. Let me put 1 at the force vector. Now you can see these are the 3 discontinuous elements, and we have not added any penalty, and that is why these are really separate. And I could add a very small penalty first. This wouldn't work because the step size is really very large. Let's add this penalty. So as you can see, this is coming closer, but it's not enough. That is because the penalty is insufficient, because this is not really being tested really well, because the step size is really very small, very large. So let's just put a penalty of 100, maybe even 25 or 50. Maybe even 25 is enough, but let's just put a high penalty. And this is our solution, in which you can see 3 DG elements which are very close. The solution is very close to your CG solution. Let's look at how we can impose the weak boundary conditions now. So let's return back here. Let's put penalty of 100 once again. Add this. And now we have to impose our weak boundary conditions. So let's look at this guy. Let's assemble a stiffness matrix first. So this guy, this is your penalty into your test function into your trial function, divided by h. So if you do that, so you could do that, you could code that, hard code it, or you could just observe that this guy is just doing the same thing, because you are imposing the boundary condition here. So in this case, I'm only looking at the boundary condition for this term, because this guy is just 0. So force vector is anyway 0. So for this case, we are looking at the boundary condition for this u1. So this would just be this guy here. So I could add this here. And I could just add this guy here. So that's my penalty. And now I should just add the penalty here as well. So let's note that this was a jump of u, right? So this was a jump of u. So the second term here was negative, and when we took it on the other side, it's just positive once again. So which means that we'll just be adding a positive contribution here. And this contribution would just be this guy here. You could just compute it once again, but I'm not doing it. So this is just p into 1 by h into your test function, which is again this test function, these three guys here, for the boundary at the left. Right? So for the boundary at the right, we do not need to add anything because we can do the same thing, but it would just be scaled with 0. So we can just keep it as 0. So let's just add this. Now you can see, again, you have the same solution, right? And just to be consistent, let's also add the last term. So this term. So this is epsilon, which is 1, and n dot del v into u. So there is no average here because there is no test function on the other side, which means that you would again have this guy just multiplied by 2. So let's just do that. Let's just 2 into this part. We'll subtract this here. Subtract this here as well. No. So on the other side, we just have to subtract this term. Should be 2 into this matrix. Right. This is the term we would subtract here for our weak boundary condition. Right. And now we have to add a contribution here. So I have shown a negative sign here, but really this depends on which side of the boundary you are in. But this guy would be positive because we are again breaking a jump function. So whatever we are, if we are subtracting here, so we have to add here. So this contribution is epsilon, which is 1 into n dot del into gradient into your, okay, so this is basically just your epsilon, which is 1, n into gradient, which is just this, into -1 for your left boundary, for this boundary -1, into just your Dirichlet boundary condition, which is 1, so we would just add this guy here. And that's it. So we have got our solution. So what would we do for a source term? So I have a vector here added for the source, which is just your constant source. I've kept it as 10 and just multiplied by your test functions. Just this is really similar to our continuous Galerkin case. So we could just add this source here as terms here, here, here. And we could just assemble the force vector. We could just take a sum of these two. And then the solution vector, could just multiply the inverse by this guy. And this would be with a constant source of 10. And we can also plot, so I've given the analytical solution here as well. Source equal to 10. So this comes from our previous Excel sheet. Right. As you can see that both of them are very close. So this is our analytical solution and this is our DG solution, these three elements. So this is the symmetric interior penalty method which we use for assembling our DG solution. And now let's have a look at the advection equation. So let's have a look at how we create a formulation for that, and that we'll not solve on an Excel sheet because we have to do time stepping. So we'll just I'll just present it on MATLAB and I'll provide a code. I'll also provide scripts in Python and Julia which you could use. And with that we would end. Maybe we could have a demonstration of the convection diffusion if it's possible. But that's it about DG for the elliptic case, and let's meet again for DG for the advection case now, which is our hyperbolic case.